Okay, and the problem is I'm going to go ahead and highlight some of the important data. So we have 100 kilograms of water, 75 degrees inside, 20 outside, 1.3 square meters of area on this heater. And we want this to insulate so that there's less than 3 degrees C drop per hour in the temperature. So they give you some suggestions about how to simplify it. But I'm going to go ahead and do a sketch here. So we have this vat of water. There's 100 kilograms. Inside, the temperature is 75 degrees C and 20 degrees outside at ambient temperature. Okay, here's the water, 100 kilograms, and let's see, we want the heat transfer to be such that the temperature drop is actually less than 3 degrees C per hour. Okay, we're going to have to convert this to some sort of heat flux value. Oh wait, I think I've forgotten something here. There's a convection on the outside, and there's also a insulating layer, which I need to draw in here. So let's see here. I'll go ahead and use this sketch here to show that there's an insulating layer, and if we were to zero in on this here, we have this wall of our material. We've got water on the inside at 75 degrees Celsius. Here's our insulating. We don't know what the K value is. That's the thing that we want to figure out, and we want to figure out the thickness. We have this convection on the outside, but we're going to call that negligible for now and come back and check it later. So we have 20 degrees C on the outside. So we know there's a steady state heat flux from this hot water to the outside. We don't know what that Q value is, but we want to make sure that the Q is such that we have less than 3 degrees C per hour drop in temperature. So let's go ahead and figure out what that corresponds to in a value of Q. So okay, the temperature drop, of course, is an indication of the internal energy drop. It's 3 degrees C per 3,600 seconds per hour, and we'll use here 4.184 joules per degree C, which is the heat capacity of water per gram. And we know we have SI units converting 1,000 grams to kilograms, and we know we have 100 kilograms. So let's go ahead and kind of keep track of these units. Cancel the kilograms, degrees C, canceling joules per second. Right now it looks like we have. So our heat flux rate, let's see, I've got 2 zeros here. I'm going to get rid of these 2 zeros. 3 over 36 is 1/12. And this is 4,189 joules per second divided by 12. It's, I don't know, 3,500 roughly. Let's see, I'll use my calculator. 349 joules per second is the heat flux that is the maximum here. We want it to be less than this. So we've got some choices, and once again we're ignoring the convection. We're going to come back and check this. We're looking at a steady state rate, so a linear temperature profile. So Q in watts per meter squared is negative K delta T delta X. Across here, we don't know X, and we don't know K, and we don't know X. So do we know this Q? Well, we know that we have joules per. We have watts, but let's go ahead and convert that to Q, little q. So watts per meter squared. We'll take the 349 watts divided by the area of the thing, which is 1.3 square meters. So that's 200 something. Calculator. 268 watts per square meter. Okay, so this is our maximum heat transfer out of this thing. So now we need to go back and select the parameters for the thickness of the insulation and the insulation type. So Q, 268 watts per meter squared must be greater than, okay, negative K delta T delta X. I'm just going to drop the negative because I know that the gradient is from outside to inside, inside to outside. 75 minus 20 over the thickness L. So we have 268 times L must be greater than K times 55. So K, it's times what, 4 over 4. Calculator, 4.89. So 4.9 here. We have one significant figure in a lot of these numbers, so I could just call this 5. L is greater than K. So here's where I need to start making some choices. Let's see, I should probably keep track of these units. So we have watts per meter squared, degree C, and the length must be in meters. So our K will end up being watts per meter, degree C. Okay, so what's a reasonable length? I'm going to say, I don't know, 2 centimeters for a wall thickness, for an insulating wall thickness, and then see what the K gives me and see what options I have. So here I have 5 times 0.02 meters. Watts per meter squared, degree C is greater than K. And this gives me roughly 0.1 watts per meter, degree C must be greater than K. Now, I'm going to go to our textbook to see what kind of options I have for K when L is 0.02 meters. Okay, this is from your Appendix A. And what I want to point out is just sort of this column right here, which is thermal conductivity. And looking at the values right here, there aren't a lot of materials, at least in this particular list, with a K value that's less than 0.1. In fact, there are none here. Then how about this list? Let's go over here. We don't see any. No. Here's something. Corkboard. All right. Well, if it's made of corkboard, it might work out. And here's another one. Glass wool. Very similar to fiberglass. Possible. Here's another. Kapok. I don't know what that is. If we make it out of lunar surface dust, apparently that will be sufficient as well. Let's see. And how about on this one? Okay, so here's some magnesia. Oh, insulation. Okay, so some insulating materials. It looks like it's going to work for those with the 2 centimeter thick insulating layer. What else? Expanded polystyrene might work. Rock wool, I don't know what that is. So as you can see, silica aerogel, wow, expensive. So some of the things, some materials will work, such as cork, magnesia, balsa wood, apparently, sawdust, perhaps glass wool. A number of things could do if we wanted the thickness of the wall to be 2 centimeters or less. Okay, the last thing we have to do is check our assumptions. Now, you recall that we assumed that the temperature drop in the steel and in the convective layer on the surface was negligible. So let's go ahead and check that out let's model this as a set of series resistors. Okay, so the initial steel wall is a single resistor, and I'm going to pick a different color here. So this wall is a resistor, the insulating material is a resistor, as this steel wall is a resistor, and then the convective wall is a resistor. So these are resistors in series, and we'll find that this will be a good assumption if pretty much all the temperature drop occurs over the main insulator. So here I've recreated the resistors, and just kind of to recall, this one is for the convective layer, this is for the steel layer, this one is for the insulating layer, this is the steel, and then here's the insulating layer, and then the other steel layer up against the water. And we need to evaluate the relative resistance of each of these. So let's see. I will, if the main temperature is dropped here over the insulating material, then we know it's a good assumption, and all the areas are the same in these. So we could take a ratio of the resistances just to look at how the relative size. Now I'm trying to get, let's see, okay, yeah, so the H, I'm pulling a value in your book from another problem, so it's roughly 3 watts per meter degree C for air, standing air. So the resistance is 1 over 3 watts per meter degree C. And for the steel, I'm going to say, 2 millimeters thick. That's pretty thin. I guess it could be a little bit thicker than that, but it's probably not a whole lot thicker. For steel, it looks like the conductivity is on the order of 60s, 30, 40, 60s. And let's see. Over here, yeah, stainless steel on the order of 10s, 20. So let's see. For a value, let's just kind of pick worst case scenario using about 60 watts per meter Kelvin. Could be smaller. I guess that's not the worst case scenario. I guess it would be stainless, like around 20. But in any case, what you can see is when you begin to compare the steel resistance with that of the insulator. Okay, I'm just going to approximate these about, basically 1 over 60,000. This is about 2 over 10, about a fifth. And what you can see is this is about a third. So in the end, it looks like this could be a good assumption if for the steel, but not so much for the convective layer, because you can see that the resistance of the steel is a lot smaller than that of the insulating, but the resistance for the convective layer is about the same as the insulating layer, so that's not a great assumption for that.